Okay, this video is mainly as a review for Science 10 up to the point where we're at right now. However, this is going to be good for both the people who are joining us brand new, as well as for those who joined partway through and those who've been here the whole time. So, this first page, this is just kind of going through your workbook a little bit. This is meant to be in conjunction with your notes booklet. I may talk about those in another video, but the main part of this is just going to be looking through this booklet and talking about what we need to talk about. So if we look at this whole list on page C2, we talked about this stuff as a group, but we haven't actually done this page. So this is a good one for you to try. My recommendation would actually be pause the video and go through this and see what you come up with, and then turn the video back on and go with it. So pause the video, give it a try. So hopefully you've paused, and at this point here, let's quick go through. I'm going to put a P for the ones that are physical, C for the ones that are chemical. So P, driving nail with a hammer. We have a nail, we have a hammer, we have a piece of wood. There's no chemical change happening. We're moving the nail, we're splitting the wood, but we haven't created any new products. All right, boiling water, also physical change. We're going from water as a liquid to water as a gas, but there's definitely no chemical change, it's still water. Frying an egg, this is chemical. We are going from a raw egg to a fried egg. You can't reverse that, but also we are doing chemical things to change the actual protein structure. Fermentation of grapes, also a chemical change. Fermentation of anything is a chemical change. Football moving through the air is a physical change. It's moving, but that's what all it's doing. Water cycle is a physical change. Aging paper turning yellow, this is a chemical change. Chopping wood, this is a physical change. Really not undoable, right? It is still something that's more or less irreversible, but it's just wood. We've changed the shape of it, we've changed the size, but we haven't changed it from being wood. Burning wood, on the other hand, is a chemical change. Iron rusting, chemical change. Leaves turning yellow in the fall, this is also a chemical change. Whipping a container of cream, this is a physical change. We are adding air to it and mixing it, but we're not actually changing the chemistry of what's going on there. All right, so let's move on. On this page here, lots of stuff here that goes with what we have in our notes as well. But we have John Dalton and his billiard ball model. We have J.J. Thomson and his raisin bun model, or sometimes known as a plum pudding model. We've got Hontaro Nagaoka's theory, where basically the atom is a positive sphere with some kind of a ring of electrons around it, which then takes us on to Rutherford's model, which is often similar idea, like a planetary kind of model. Difference between Nagaoka and Rutherford would be that with Rutherford, there's more than just one place where the electrons can be. Bohr gets more precise with where the electrons are. And so we can have this idea of 2, 8, 8, and then complicated. It's sort of 2, 8, 8, 18, 18, 32, 32. But once we get beyond 8, and even with the ones with that have the 8, we have some more complexity that's there. And one of the places that complexity shows up later on is if you look at something like iron or manganese or nickel. What you see is there's more than one possible ion charge, and those possible ion charges actually for the metals come down to the fact that there are subshells. And so within the, for example, in the fourth period, within those 18 elements in that fourth period, there are definitely, there's a 2, a 10, and a 6 in terms of subshells there. And so it gets more confusing. So we generally go 2, 8, 8. We can say the first one, the next one's have 2. That takes us up to potassium and calcium. But really beyond that, it becomes somewhat confusing. And so we usually just leave that alone. So 2, 8, 8, and then confusing. and complex. And then we've got the quantum mechanical model with Schrodinger, and this is a very probabilistic model. The idea would be like if you have rotating fan blades, you know if you stick your hand in there, it will eventually get cut. But exactly where the blades are at any one particular point in time is hard to say. We just say that there's a high probability that the blade will be there at some point. It's very, very mathematical. It gets some really confusing looking math stuff that is definitely well beyond high school math. So it's there. You should understand that it is a probability pattern, but you don't have to understand more than the idea of the electrons are mathematically described, and it's probabilistic, but it's definitely a challenge. Moving on. We talked about the idea of atomic number and mass number. Now, if you look at your periodic table, the mass number and the atomic number and the number of protons and neutrons, you can actually discover most of those. Now, the atomic number, this would be if you look, for example, at iron. Right, you have Fe in the middle. Usually it'll say iron bottom. And then the top left will be 26. This is the atomic number. And the atomic number, it's supposed to be a B, is also the same as the number of protons. So these two columns on this chart are the same. Now the number of neutrons, you have to understand the idea, but the number of neutrons is something that is specific to an atom. It will always be a whole number. And if we want to find out the mass number, we add neutrons plus protons. So if I add those two, I get the mass number. And we use the mass number to help tell us the isotope. And the isotope is going to be, this here would be carbon 14. Now, if I have something where I had, for example, carbon 12, let's look at that one. It also has an atomic number of 6, which means it has 6 protons. The 12 here means that my mass number is 12. And the number of neutrons is basically 12 minus 6 would get us there, so it's going to be 6. Or what plus 6 equals 12. All right? And so with your number of neutrons, you're going to be either told that or you'll have a mass number and you'll be able to have to move it there. So again, another practice one we could look at would be, let's look at number 12 on this page here. Tells us that we have number of protons is 20 and 21 neutrons. Now right away, 20 plus 21, that's 41. It tells me my mass number is 41. The number of protons is 20, which means atomic number is 20. Then I look on my periodic table, I find out that is calcium. And so this one, I would write down the name of it would be calcium 41. Right, and again, this is not the same. You'll notice the 41 is not the same as the 40.08 that's in the top right-hand corner of the calcium square. We're going to talk about that in a little bit, and then lots more of the intermediates. All right, so atomic mass is where we look at all of the different isotopes. And we should understand that, for example, in this question, it's referring to 63 Cu and 65 Cu. These are both isotopes of copper. We could also write this top one as copper-63. That's the same notation as the previous page. This would be then copper-65. It's a weighted average of all of these. And so what you're going to do to figure out the average atomic mass, this average atomic mass, that is the number in the top right-hand corner of the square. So for copper, this theoretically is going to work out to 63.55, although sometimes on a test, what you're going to find is that it's going to be slightly different to make sure that you actually know what you're doing and aren't just copying the answer. So in this case here, we would say, okay, relative abundances are this this, which means if I want to find the average atomic mass, I am going to say, well, my average atomic mass is going to be equal to, so I've got 69.1% of copper 63, so it's going to be 69.1 times 63 plus 30.9 times 65, and then that's all divided by 100. And I end up with my weighted average there, and we could do the calculations, and we would find out what your average atomic mass would be. And my calculator apparently is an MIA, so I will not do this calculation right now. That's something that's easy enough for you to do. All right, and you can do the same thing with more complex things, and that's what's here. This little chart here, same as before, except we add this column here with number of electrons. And if we are dealing with an atom, which this is for all of them, atomic number, not mass number, sorry, protons and electrons are always the same. Mass number is always protons plus neutrons, and then the symbol is just off of the periodic table. So looking at this very first one, just to give you an example of the type of stuff you're expected to do, if I have an atomic number of 7, that means I have 7 protons, which means I have 7 electrons. My mass number is going to be protons plus neutrons, so it's 14. And then the symbol of this element would be nitrogen, and that's all I need to have here. If I wanted to be very picky and precise, I could actually say this is nitrogen, and then a subscript on the left side, 14, because that is its mass number. If I want to do the physics 30 thing, I also put the atomic number at the bottom, which would be a 7, but that is well beyond science 10 at this point. Okay, if I look at part B, I've got 9 protons, which means my atomic number is 9. 9 plus 10 gives me my, so protons plus neutrons gives me the mass number, which is 19. Protons and electrons are the same in an atom, it's 9. I find that on the periodic table. It is indeed fluorine, and so the symbol is F. Right? Something to continue working on. Bohr models, as I mentioned earlier, we can draw Bohr models, and there's this idea of the 288. That means when we look at our electron diagrams, in the first electron shell, we can have a maximum of 2. So that's what we've got here. Second one, a maximum of 8. Third is a maximum of 8. The fourth one could have a maximum of 18. You will never be asked to do more than 2 in the fourth one. So there we go. Now, if I have potassium 39, the fact that its mass number is 39 is almost completely inconsequential. But the way I would go figuring this out, the 39 does tell me in the nucleus I have 19 protons and 20 neutrons. Sorry, 19 protons, 20 neutrons. So 20 plus 19 is 39. It has to have 19 protons because it is potassium. And then because it's potassium 39, 19 plus what would give me 39, and it is indeed 20. So with this one here, how do I go about figuring that out? And if I wanted to draw it for myself, what would I do? Well, I would say, okay, this is potassium, so I have 19 protons. I have 20 neutrons, and I can just do like a little sunset thing here. The first one can have a maximum of 2 electrons. We need to have 19 in total. Okay, so maximum of 2 in the first one, it's full. We always start from the middle and fill them up. The second one, maximum of 8, it's got to be full as well. Third one, also a maximum of 8. I double check here, 2 plus 8 is 10, plus 8 more is 18. I need 19, which means in my fourth one I have 1 more. And away we go. You can fill in the rest of this. Group, this is the column on the periodic table. Period, this is the row. The rest of it you can figure out. As we continue here, you can see this is a way to look at a periodic table. Ours doesn't have this stuff on the side where it tells you the number of electrons at each energy level. But other than that, it pretty much has the same information. One thing you should know as well, you look on your periodic table on the far right-hand side, we have the noble gases. And the noble gases are special. They're not excessively reactive with much of anything, and they all have full energy levels, and that's important to know as well. All right, let's move on to C17. All right, so C17, this is actually something that I got everybody to do in their notes. You can do something essentially like this. This is where you go through and you're going to write down a quick energy level diagram for each of the atoms. Now, I am not going to have you worry about the number of neutrons in the nucleus. We do not need to worry about that. And you should be able to answer these questions then. We did discuss them. This is in your book. It'll be easier to do than watching it on the video. The thing to remember, though, is the first period can have a maximum of 2, and then a maximum of 8, and then a maximum of 8. And we always fill them in order. So give that a try. That's going to be something I want to see from each of you. This is looking, now the whole thing in terms of this classification thing, very useful. In terms of the groups, we use actual numbers instead of these Roman numerals now, and that makes life a little bit easier. However, you need to know alkaline metals, alkaline earth metals, transition elements or transition metals. You need to know that there is a staircase line here. All right, to the left of it is metals, to the right of it is non-metals. You need to know the noble gases. You need to know halogens. And you should understand lanthanum series and actinium series, or lanthanides and actinides. Right. We will be talking more about classification stuff later on, so don't stress too much about that. A lot of this should be reviewed from previous years anyways. All right. Looking at the periodic table, again, horizontal shaded band, this is a period. I'm going to say, and I'm not going to write them, you'll have to pay attention. Number 2, vertical shaded band, or any other vertical shaded band, is a group or a family. Extended form of the periodic table puts the lanthanide series and the actinide series into the main body. You can see my version of this in the classroom. I actually moved 3 to where it should be, which is next to 4. Other than that, it should be good. We've got alkali metals in number 3. We have alkaline earth metals in number 4. We have halogens in number 5. We have noble gases in number 6. We have the dark shaded areas, the staircase. These are the metalloids. Light shaded area over here are the non-metals, and the non-shaded area would be the metals. Notice that hydrogen is in there as a non-metal. If I look at number 8 here, we're looking at the transition metals. Number 9, we've got the lanthanides and the actinides. And then here's just using groups and periods and things like that. SATP, this is it means standard ambient temperature and pressure. Essentially, it's room temperature. And you'll use your periodic table has all kinds of useful things to tell you what their state is at room temperature. That is the first part of our review. Getting you used to the periodic table. Just double check. You can also fill this one in with the exception, you'll have trouble with number 15. It's not impossible, but, and then these two here, uranium and erbium, we only have one name. We're not using some of the older ones, so it's either lanthanides or actinides for those ones there. Other than that, hold on, make sure I'm not lying to you. Yeah, that is the first part of our review. Is just up to the end of up to periodic table. No worrying about ions quite yet. All right, thank you.